Hey everyone, welcome to your Algebra 1 play posit for the day. We are going to be reviewing and refreshing ourselves on Unit 4 after the break. So go ahead and grab your notes, have your OMHS play posit graded assignment open, and let's get started. Just one quick announcement. You may have seen this in the newsletter already, but coming up pretty soon, I think it's 2 weeks from now, we are having our Wonderland of Gingerbread Assembly on Friday, December 12th. I'm so excited. Each grade level has a different time for that assembly. 7th grade's at 11 and 8th grade is at 1 p.m. on that Friday. This is optional, but it's so much fun. So if you guys have access to materials to create a gingerbread house, it can be anything from graham crackers to actual gingerbread. This year I'm going to use Pop-Tarts to try to build mine. You can even design your own on paper if you don't have access to those materials at the time. And we just want you guys to submit your photos and description via the Google form. So I can't share the Google form through this play posit with you, but I'm going to have it on your course page. And then also, like I said, you can find it in the newsletter, and I'm sure you can find it other places. Your teachers are going to be sharing this link in class. But if for some reason you can't find it, send me an email and I'll send it to you. And we want those in by December 7th, just so we can compile everything. And if for some reason you don't want to submit your design, you don't have to, but you can still come for the fun of seeing all the other designs that were submitted. And we're going to have some prizes for 2 different categories, some voting options. So hope to see you guys there. Here's our first review for Unit 4. Remember, identifying functions. So there's a few different ways that we looked at functions. Here's one of them. It's a mapping diagram. So the domain is mapping to the range. Remember, the domain are the x values and the range are the y values. So here we have 10 mapping to 18. So another way to think about that is it's a coordinate point, 10, 18. And 0 maps to 20, so 0, 20. So a mapping is just another way to write coordinate points, or another way to write a table, or another way to write a graph. So they're all just different ways that you can represent a function. So is this particular relation a function? What do you guys think? Yes, this is a function. So our x values do not repeat. So if you were to kind of plot these points on a coordinate plane, we can kind of estimate here. Here's 10, 18, 0, 20, 7, 2. I'm just sort of estimating. 4, 10. You can see that none of these points are on top of each other. If we were to do that vertical line test, that line would not hit that point more than once. So yes, this is a function. Okay, and over here in the second example, I'll label these 1 and 2, we can see how functions are displayed graphically, visually. So in these scenarios, I think it's easier to use that vertical line test. So for example, if we were to draw a vertical line anywhere down this graph, you would see that the line would only hit the graph once, which means there is a unique single x value for this point on this graph. So this is a function. But look at this guy here. Look, you guys can probably already see there are 2 x values. I'm sorry, there's 1 x value for 2 different points on the same graph. So this is not a function. So this is -2, and this is 1, 2, +2, and this is approximately, I'd say, -1.5. Kind of hard to see there. So if we were to list out these coordinate points, it'd be -2, 2, +2, and -2, -1.5. So you can see the x values do repeat, which means it is not a function. Same thing here with the circle. Circles are never functions, and this line is a function. All right, now we're going to talk about domain and range a little more specifically. So domain are the x values and range are the y values. That's it. So when you're looking at this first example, if it said find the domain would be all the x values. And we typically list numbers using these curly brackets, and we list them in order. So there's our x values. And you might also see it like this because they don't, for domain and range, you don't necessarily need the duplicate values there, but only for domain and range. I don't want you to think that you can leave numbers out like if you're listing coordinate points, right? Because these 2 points are 2 different values. But in the domain, 0 is a value in the domain, period. It is. So whether you have 2 zeros listed or 1 0 listed. The range are the y values. So we're just going to pick off the y values from those coordinate points. There we go. All right, if we look at example 2 here, again, the domain are the x values and the range are the y values. So the x values in this example are, we just got to pick them off the graph, -1, 0, 2, and 3. Those are all the x values in those coordinate points. And the range are those y values. So +2, hold on, I might need to reorder this once I list them out. +2, we'd have to go this way. -1, 1, and 5. So let me just relist this. It's just proper to do it in numerical order. There we go. Now we get into evaluating functions. Before I go any further, I know that we're watching this in PlayPosit, but if for some reason, even when you're in PlayPosit, or if you're watching it as a ViewPure link, don't forget you can always press pause if you're filling in your notes or you're trying an example on your own, and then come back and press play. So don't forget that. So here they give us a function, f of x equals x plus 7, and they want us to evaluate. So the first one says f of -1. So that means we're going to take -1 and we're going to put it in everywhere we see the x. That's it. And then you guys can do that numerical math. So this is 6. So f of -1 is 6. So you can write this as a coordinate point also. Remember, the x value is the input. See how the -1 is inside the parentheses? That's the input. And the y value is the output, the -6. So you always have x and you have f of x. Remember, f of x is just our new way of saying y. It's called function notation. And you're just going to see it a lot more as you get into Algebra 1 and Algebra 2. Because you can do more things with it, like this. We can do evaluating functions and find outputs given a specific input. If you just had y here, I mean, I guess you could say, like, let y, or find y. So it's just a different way to write it, f of x and y. So let's try this one. F of 10 means you put 10 in wherever the x's are, and we have 17. So that means there is a dot on this graph at 10, 17, this particular graph. Now this one's a little reversed. It says find x when f of x is 12. So remember, this is y. They want us to find the x value if y is 12. So we do the same thing, except we put them in different places. So f of x is 12, so instead of f of x, I'll write 12. And then we're trying to solve for x. So this takes us back to old school. Now it feels like old school, right? Solving equations. So we want to get the x by itself. So we have to get rid of everything else with the x. So how can we move a +7 to the other side to get the x by itself? We do that inverse operation. We're going to subtract 7 from both sides. So you get x equals 12 minus 7 is 5. So again, we can write that as a coordinate point if we wanted to. I'm not saying you have to, but just keep in mind that that's what you're getting, right? You're getting that coordinate point on the graph. So we can also evaluate functions graphically. So this time, they don't give us a function rule. They don't say f of x equals something, right? We don't know what f of x equals. Sometimes you could figure it out if it's a common graph, something that you're used to. But this graph, we are definitely not graphing these in this class. It's It's all kind of all over the place, right? We've graphed lines, and you guys will see we're going to graph circles at the end of the year. But we're not graphing. This is a piecewise function. There's multiple parts. So we have to use the graph. We have to use the picture. So remember, this is f of x. So 5 is the x value. So they're saying, okay, if x is 5, what is y? So let's just go to the graph at x equals 5 and go up to the line and say, well, what is the y value there? Oh, it's 2. 5 comma 2. So when x is 5, y is 2 on the graph. Let's try the next one. -4 is the input, so they're saying, okay, if x is -4, what is y? So we just go on the x-axis at -4, go up to the graph, and say, well, what is y at this point? It is 7. There we go. And last one, similar to that last slide, we're going to reverse it on us. This time they give us f of x. This time they give us y. So find x. What is x when y is 4? It's kind of reversed there. So we're going to go on the y-axis at 4 and say, well, where does the graph exist? The graph exists here. Let's say that's on that grid mark for ease. And the graph exists here. So there are 2 different places where y is 4. And it happens at x equals 1. And it happens at x equals -7. So there are 2 different places that the graph exists at y equals 4. Here and here. And they wanted us to pick off the x values. So is this a function? Yes, this is a function. 1, it passes the vertical line test. And then also, just to kind of make an example of it, over here, the y values repeat. That's okay. The x values do not repeat. So this is a function. Speaking of functions, let's review graphing. So I know that we have our Desmos calculator, and I'm going to show you guys this on the Desmos calculator. But we also want to review it by hand, because I know that some of us have gotten into some issues with the OMHS tests. You know, you guys are getting decimals for your points that you want to graph, but OMHS does not take decimals. They want your answer to land on a grid mark. And that's sort of just a programming situation. Like they're not going to be able to program and check your solution if it's a decimal. So let's just review how to graph these by hand, and then also we'll look at Desmos because you can use that as a tool. So this function is in our very happy y equals mx plus b form, right? So b is our y-intercept. That's where it crosses the y-axis, and m is the slope. That's the rise over run. So let's start with the y-intercept. We know for a fact that this graph is going to cross right through -4. So I'm going to put a dot there. We know that there's a dot there. Now let's just use the slope, 2/3. So that means we're going to go up 2 over 3. So up 2 over 3. See, that gets us a point on another grid mark. You can keep going if you want. When you're doing this in the OMHS, you only need 2 points. And then you're going to, when you do it on the test, it automatically connects the dots for you. So here, I'm going to connect them. Ta-da! Now let me show you guys on the Desmos and what can happen. I'm going to pull that up. I should have this. I know I have it as a favorite. Okay, now you know me, I forget what it is. 2/3 x minus 4. So you go here, you're like, okay, I'm going to graph this. One, Ms. Winslow said I could, and I have a tool at my disposal, so why not graph it? Right, so -4. Now this one just happened to be nice, but let's say you're like, okay, I need to take this and I need to put it into the OMHS, right? So, oh, I know it goes here, but then you want to put it like on 2.04 or -2.06. OMHS is not going to take that point. You need to keep looking along the line to find another whole number grid mark, Oh, here's one. You could put it on 6, 0. Or, oh, here's another one. You could put it on, it's very, you could put it on 12, 4. So if you use the Desmos calculator, I want you guys to be careful as you're translating that back to your OMHS quizzes and tests. Just make sure you're finding whole number values along the line that you graph, because it will count it wrong. Now, if for some reason you forget what I'm saying and you graph it and you see the answer and you're like, wait a minute, I got that right, and basically the computer counted me wrong, please send me an email and I'll look into it. Most of the time I can just give you the points back, because computers are not perfect, neither are we, so we need to work with them. Here is another one. So they want us to graph this, and again, you might go to Desmos and graph it, which is perfectly fine, but let's do it also by hand. Okay, if I could get my pencil. There we go. So this is in point slope form, because we have a point right there and we have a slope, that -2. So this is called point slope form. So you can get a point. -3 is with the x, so that's the x value. And remember, when you pick it off of the formula, you do the opposite sign. And -4 is with the y, and it'll be a +4. If you guys remember, here's the general form of this. M times x minus x1. And this is basically the reason why we always take the opposite sign. It's because there's a negative in the formula, in the general form. So if you were to put these numbers, if we were sort of to translate that back into this equation, this plus would become a minus. This minus would become a plus, right? Because a negative times a negative is a positive. So that's sort of another explanation why we switch those symbols. If you don't need the explanation and you just want to remember, I flipped the sign. That works for now too, because you guys will learn more about this in Algebra 2 as well. All right, and then the slope is -2. So now we have everything we need. We have a point. So I'm going to go to -3, 4, put a dot, and then we have our slope. I'm going to go, ooh, so this is a whole number. Remember, you can always write a whole number as a fraction. That'll help with the slope. Go down to over 1. Down to over 1. See, these are all hitting on whole numbers. Of course, there are decimal values in between here, right? But it's going to be easiest to graph, and the computer is going to accept whole numbers. So let's look at this in Desmos to see. I bet you this one will give us more decimals. Y minus 4, and you can put it in as you see it, which is cool. Oh, I forgot that very last number. You would think x plus 3. There we go. Here's our line. So you can also sort of just take a glance at it and make sure that it matches what you graphed, what we graphed. And sure enough, it does. They're both going down from left to right. And if you wanted to find some coordinate points, we go on the grid. So here you can see that is a point on the grid, but you don't want that because OMHS is going to count that wrong. So just kind of keep scrolling. Oh, there's 1, 0, -2, -1, 0, -2, 2. These are all whole number grid points that you could use to graph this line. All right, analyzing graphs, my favorite. I love this so much because I feel like it just gives what we're studying a little more purpose, right? To be able to analyze graphs. And with everything going on in the world, or just in general, I mean, you guys probably see statistics and data and graphs everywhere you look on Facebook. I know I do. Maybe that's the analytics on my Facebook page, but I see tons, just the media trying to put out information for you to absorb and take as facts. So the thing about analyzing graphs is you have to be careful, right, to get the accurate information that the graph is trying to give you. Basically, it's telling a story, and can we read the story of the graph? Now, in semester 2, the very last thing we're going to study is statistics, and it's going to be so much fun. Some of you are probably going to love it and some of you might despise it. I love to hate it, or I hate to love it. I don't know. You'll hear more about that as we get there. But basically, we need to make sure that we're hearing the story the graph is telling. So right now, the graphs we're studying are a little more, face value. What it's showing is what it is. So we can't massage the numbers very much. But as we get into semester 2, you'll see what I mean. Here's our first graph we're going to look at. This is Mika's essay graph, and it shows that the number of hours Mika spent writing her essay depends on the total pages written. So this makes sense, right? You would expect the more time you spend writing a paper, the more pages you're going to get over time. So this graph makes sense, right? So what is the y-intercept? That's where it crosses the y-axis, and it is 5 pages. So what does that represent in this scenario? Well, you could say, when she sat down for this period, that's how many pages she started with. We know that this y-intercept in these examples is always sort of that starting value, the starting point. Sometimes the starting points don't make as much sense as other times, right? I mean, we know that she didn't just magically have 5 pages of writing appear out of thin air, right? She obviously spent time on that. But maybe she had those pages before she started tracking the hours spent. Or maybe those 5 pages are sort of like a preface, how you say that? A preface to her page, to her paper that her teacher required and her teacher gave them to her. I don't know. We could speculate all day long how she got those 5 pages, but nonetheless, it's her starting point. She started with 5 pages for this particular project. So what is the slope? So remember, we always want to be careful when we're looking at real graphs, I guess any graph, to look at the increments that the axes are going. So our x-axis is going by 1, and our y-axis is also going by 1. That's nice when they match. So we can sort of take this for what it is, right? We're going to go up 1 over 1, up 1 over 1. So the slope is 1 over 1. But what does that really mean? This is where it gets cool, right? We're not just saying slope is 1. Well, okay, but that's boring. What does it mean? In this scenario, it means, and the way I find this, if you ever get stuck on these, here's a really helpful tip. Go to the numbers and put labels on them. So we know that slope is rise over run. That's the change in y over the change in x. So y is on the top. So the y values represent what? Pages written. So 1 page written over 1 hour spent. And that's it. I mean, that's what it means. That's the meaning. It represents that and you could rephrase it. You could say for every hour, Mika writes 1 page. That's kind of the explanation. For every hour, Mika writes 1 page. And that's just this example, right? It's going to depend on the slope. All right, our last question here. After spending 1 hour this week, how many pages will Mika have? So we go to 1 hour, we go up to the graph, and after 1 hour, she's going to have 6 pages. So this is sort of another way to do function, what we did up here, look. Evaluating functions from a graph. So you can also do that in real world scenarios. So we could also write this f of 1 equals 6. So 1 hour is the x value, that's the input, and the output is 6 pages. Cool. So looks like, it's funny because this graph goes on forever. You might not expect that of this example, this project. I wouldn't. You'd think there'd be an ending, but maybe not. Maybe that indicates it's a sequel, right? All right, so here's another example. This graph shows how much, the amount of peanut butter Larry has left is related to the number of sandwiches he makes. Fun fact, I despise jelly. I have no idea why. And my brother despises peanut butter. We both like the opposite. I don't know, something about jelly's texture, it's strange to me. But this graph is just talking about peanut butter and the number of sandwiches that we can make. And this graph does go down from left to right, which is what we would expect, right? We're using something, so it's going away. So here's the y-intercept is 10 for number 1. And just like the other ones, we know that that's the starting point. The starting value of 10 what? 10 ounces of peanut butter. So this is a case where it makes super sense, right? He has a jar of 10 ounces of peanut butter. He went to the store or had groceries delivered, and it's a 10-ounce jar of peanut butter. Or maybe it's a 20-ounce jar of peanut butter, but this time, this moment, when he sits down to make sandwiches, he only has 10 ounces remaining. Nonetheless, just like the previous example, it is our starting value for this problem. What is the slope? Our increments are also the same. They go by 1 in both. That's nice. So we're going to go down 1, 2, 3 over 1. Down 3 over 1. So our slope is 3 over 1. What does that represent? So remember, we can do labels. 3 ounces of peanut butter per 1 sandwich. So it takes 3 ounces of peanut butter. I've been using PB. I hope you guys caught that. To make 1 sandwich. Of course, this is just an estimate. This is the amount of peanut butter it took Larry to make his sandwich. Your sandwich could vary, but we're saying on general that he's going to give a 3-ounce amount of peanut butter on each sandwich. So how many whole sandwiches can he make before his peanut butter runs out? This could be like a legitimate question you'd ask yourself. I don't know that I would sit down and make a graph for it if I was grocery shopping, although I might. But you guys, we kind of do this already in our head. We do estimates, right? If you have to make a grocery list, you go into your cabinet, you say, oh, ooh, I only have about this much peanut butter left, and I know how many sandwiches I typically eat. Am I gonna have enough? So that's this example, just more specifically done with values. So how many whole sandwiches can he make before running out? Well, our number of sandwiches is along the x-axis. So you can see 3 sandwiches, and then, oh, he can make, looks like he can make like 3 1/4 sandwiches, right? About. But we want whole sandwiches, so we're going to say 3. He can't make 4. I mean, I guess you could argue he could make 4. It would just have less peanut butter in it, right? I would take that answer if you were turning something into me. But if you're answering this on a test or a quiz, the answer would be 3 sandwiches, closest to the whole number without going over. Lastly, if Larry has a 6-ounce jar of peanut butter in the pantry and 3 friends coming over, can everyone have a sandwich? Let's just say, can everyone have a sandwich? So he has 6 ounces of peanut butter. Let's go to the ounces of 6 right here. How many sandwiches can 6 ounces of peanut butter make? We go down and see, look at the x value, and it looks like it's about 1.5. About 1.5. So we're going to say no, right? Because we need 3 sandwiches and even 4 if you count Larry. So we're going to say no. One thing I noticed here, and hopefully you guys noticed it too, this line is going down. So we do need a negative on our slope here. Negative 3 ounces per sandwich. And that makes sense, again, because you're sort of taking away the peanut butter. So it is a negative value. And you might expect that you could make 2 sandwiches with 6 ounces. But there's always a sort of estimation when you're dealing with something like this. So we want to go to the exact value on the line when y is 6 and see what is that x value. And I mean, it's almost 2, but not quite. we would still just not have enough, right? Because we have 3 friends. Okay, here's our last one. This graph shows how the cost of an Uber ride depends on the distance in miles. And this one makes sense too, right? You would expect the longer you drive in a car, you're going to have to pay that person more, an Uber or a taxi driver, either way. So here our y-intercept is $3. 3. I mean, I know we've talked about this, we can write this as an ordered pair, but when you're dealing with real world scenarios too, it just makes more sense to look at it as a single value. What does this represent? Again, it's the starting value. This one does also make great sense because it means you're going to have to pay $3 just to get in the car. It's kind of like their flat fee, right? It's the starting value. All right, our slope. Okay, we're going by ones and ones. Perfect. So we're going to go up 1 over 2. Up 1 over 2. 1 over 2. So $1 over 2 miles. So after you pay the $3 just to get in the car, you're going to have to pay $1 every 2 miles. So I kind of just said this, right? The cost is $1 per 2 miles. So what does it represent is sort of just giving the slope meaning in relation to the problem. Number 5, how much will it cost to travel 6 miles? So we'll go to the 6 miles, go up to the graph and say, oh, it's going to cost me $6. And lastly, you want a quick ride to your friend's house that's 4 miles away, and you have a $10 bill. Do you have enough money to take the Uber, or will you need to walk? Of course, with your learning coach's permission, right? Or your parents. So let's see, 4 miles. And this might actually be, I need to look this up. I should look this up to see if the Uber sites have sort of these graphs or estimation of costs. Because it's a good thing to know, right? Especially if you're paying in cash and you don't have enough cash. Like, you're not going to want to get in that car because then you'll be like, oh, I can't pay you. Never want that to happen. So 4 miles is going to be approximately $5. Of course, usually you guys, we tip these kind of drivers too. So you definitely have enough with that $10 bill to take the Uber with your learning coach's permission. All right, our last topic is on transformation. And there's something I wanted to just chat with you guys about. I noticed, and it's funny, I had no idea, it must be new this year, but I noticed that your OMHS includes horizontal stretches in the quiz for this unit. It does not include horizontal stretches in the test, so don't worry about that. But horizontal stretches are not part of our standard. That's an Algebra 2 standard. So, I mean, it's cool and it's great that we've covered it and we've like, talked about it and you guys have seen it. But we actually did not cover horizontal stretches in class. You covered it in your OMHS. So I want to say don't worry about this for the SOL. And I'm going to go back and I'm going to edit this quiz to give students points back if you missed the horizontal stretch question. So don't worry about that. But I just wanted to kind of clarify that because we do have a stretch and it's a vertical stretch. And that stretch is affected by the slope. So let's review transformations together. So the vertical shift, I'm going to just do a general function here. Is affected by the C value. So this can be any number. I just chose C. And if it's a plus C, it's going to go up. And if it's a minus C, it's going to go down. So this value is here to the right outside of any of the parentheses, and that is our vertical shift. Excuse me. All right, let's look at our horizontal shift now. So our horizontal shift is shown to us by the H value. And again, because there's a negative inside the general form, just like we've seen previously, it means you're going to take the opposite sign. So if it's a negative H, it's going to go to the right. If it's a positive h, it's going to go to the left. So you want to think positive and you want to think negative, right? Because positive goes to the right and negative goes to the left. And the h value is inside the parentheses. All right, over here, our vertical stretch. This is what I was talking about with stretching. The ones we're going to do in Algebra 1 are vertical stretches. So let me give you an example. Whoops. I'm just going to give you like, oh, we can do it this way. Okay, here. F of x equals a times some function. About that, you may have heard my daughter Sophia. Okay, vertical stretching is affected by the slope, the a value, the number that's in front here. And, oh, let me erase. I was getting ahead of myself. Oops. So, if A, we're going to have a vertical stretch if A is basically a whole number, basically. The absolute value of A is bigger than 1. And we'll see some examples. So like 1, 2, 7, 12. And we're going to have a vertical compression, or it's going to be compressed vertically, if A is a fraction. So if A is between 0 and 1, a fraction. All right, our last transformation is a reflection. So here's f of x. Here's just our general. Let me get my highlighter. So if the negative is out here in the front, then it is going to reflect over the x-axis. Okay, if the negative is on the inside, we can even put a here, right? A kind of exists everywhere. Then it'll reflect over the y-axis. So I know that we've talked about these in class, but I know students had some questions still. So I wanted to give you the general forms here and also remind you that you're not responsible for the horizontal stretches or compresses. And let's do some examples. So here's the function on the left, and we want to describe what's happening. So here we have a plus 3 outside of the parentheses. There's no parentheses over here. So that's going to be 3 units up. So it's going to take our parent function. Here's what we call a parent function. F of x equals x. It's just our very general basic starting point. This graph goes through the origin. You can graph it on Desmos. You can also graph it by hand, right? Because there's no y-intercept, so it's going to go through 0, 0. And the slope is 1, up 1 over 1. So this is called our parent function. And then we can make all these changes to it, right? Like we're doing here. We're adding 3, so the parent function is going to shift up 3 units. Let's look at number 2. We have 2 things happening, right? I see a plus 3 here and a minus 1. So the plus 3 is going to make it go 3 units to the left. Remember, that's inside the parentheses. That's that horizontal shift. You take the opposite. And 1 unit down. This number is our vertical shift, just like the 3. And you take it for what it is, because it's not inside of a parentheses. All right, down here, it looks like we have a negative and a 4, and also a negative 5. So let's do that vertical shift first. I think that's the easiest one in my opinion. 5 units down. And then the negative is right in front of the x term, right? So that's going to reflect it over the x-axis. And then the 4, that's that a value. It's not a fraction. So we would say the absolute value of negative 4 is 4, right? And 4 is bigger than 1. So we have a stretch. So basically you're asking yourself, is it a stretch or is it a compress? And the thing with the 4, you guys know that's the slope, right? The bigger the number, the bigger the slope, the steeper the line. So you're essentially taking the edges of that line and stretching it out, stretching the right side up and stretching the left side down, which is going to make that line steeper. And a fraction is going to make it less steep. Let's look at the last one, number 4. So we have the 1/2 out here on the front. That's that fraction, so we know it's going to compress. Vertical compression. There is a negative inside the parentheses this time, so that's going to reflect over the y-axis. And there's a -1 inside the parentheses. That's going to go 1 unit to the right. That's our horizontal shift. And since it's negative, you want to think the opposite. So we're going to go to the right. Okay, this time we're going to kind of go in reverse. We're going to write the function from the clues. So they're telling us the transformations, and we're going to write the function. So number 1 here, it says to find g of x. So find some new function, g of x, if we do this to f of x. So we're going to translate it 8 units down from here, from the starting point. So down, that's our vertical shift, right? And we know this is the value that affects vertical shift. So we're going to take the +2 and we're going to move it down 8 units. So think, this means -8. If we were to graph this, which we could, it would go through, here, there we go. It would go through the y-axis at +2, right there. And we would take this y-intercept and move it down 8 units. Where is the new y-intercept? About here, right? So you're taking this value and you're subtracting 8 from it. That's all we're doing. So the new function is going to be x plus 2 minus 8, which is x minus 6. That is the new translated function after we took the whole thing and moved it down 8 units. All right, number 2, find f of x. So this time we're going to take g of x. F of x and g of x are all ways to name functions. It's just another name for a function. So we're going to take this given function and translate it 4 units to the left. Ooh, the left, that's a horizontal shift. So remember, that's going to be inside the parentheses. I have x here. Here's the x that I have. And we're going to move that x 4 units to the left. So we know there's a 4, and it's going to be a plus because we do opposite, right? It says left, so we want a plus here. All right, number 3, the last one. This time, we're doing a vertical stretch of 3. So remember, a stretch goes in front of the x term. So all you do is you put it in front of the x term. That's it. You could leave it like that, or you can multiply it out. I would likely multiply it out because just like we did up here, we went ahead and did that subtraction. Okay, I hope you guys are feeling a little bit better about this. Let me know if you still need help on transformations or anything really. Coming up tomorrow, we have a Unit 4 review on your own. So that's in the OMHS and it's an actual review sheet versus, sometimes it just says review previously learned material. And you're like, what? I put a review sheet in there for you and I'll get an answer key up if I can. And then we will have live class tomorrow, obviously. And it's going to cover the very last topic in Unit 4. And then something I wanted to point out, you guys know that we have extra sessions every week with Miss Jadala. And this Wednesday at 11, she's going to do an entire Unit 4 review session. So before, right now on your plan, it says you're taking Unit 4 test on Thursday. So There's lots of opportunities to review before that test, and hope to see you guys at some of them. And I'll see all of you at live class. I can't wait. Bye, everybody.